The Transmission Control Protocol, TCP, is a fundamental component of the Internet Protocol Suite, often known as TCP/IP due to its close association with the Internet Protocol, IP. TCP ensures the secure and orderly transmission of data packets between applications operating on hosts connected through an IP network. Key Internet services like the World Wide Web, email, remote administration, and file transfer depend on TCP, situated within the transport layer of the TCP/IP suite. Furthermore, SSL/TLS commonly functions on top of TCP to provide secure communication channels. Operating in a connection-oriented manner, TCP necessitates a preliminary connection establishment between sender and receiver through a three-step handshake process. In this procedure, the server must be in a passive, open state, ready to acknowledge connection requests from clients to establish communication successfully. In May 1974, Vint Cerf and Bob Kahn introduced an Internet working protocol based on packet switching among network nodes. They collaborated with Gérard Lalande to integrate ideas from the French Cyclades project into this new network. The resulting protocol, RFC 675, known as the Specification of Internet Transmission Control Program, was penned by Vint Cerf, Yogan Dalal, and Carl Sunshine, and made public in December 1974, marking the earliest use of the term Internet to represent Internet work. Initially, the Transmission Control Program merged connection-oriented links with datagram services among hosts. With version 4, this monolithic program evolved into a modular structure comprising the Transmission Control Protocol and the Internet Protocol, shaping what was famously known as TCP/IP, although formally referenced as the DoD Internet Architecture Model or DARPA model. Over time, it integrated into the Internet Protocol Suite, broadening its impact. A series of Internet Experiment Notes, IEN, detailed the progression of TCP into its contemporary form, leading to the standardization of TCP in January 1980 under RFC 761. In 2004, Vint Cerf and Bob Kahn were honored with the Turing Award for their seminal contributions to TCP/IP. The Transmission Control Protocol acts as an intermediary between an application program and the Internet Protocol, facilitating host-to-host connectivity at the transport layer of the Internet model. TCP manages all handshaking and transmission specifics, shielding applications from network intricacies by abstracting the network connection through a network socket interface. In the event of network congestion or irregular behavior causing IP packets to be lost, duplicated, or delivered out of sequence, TCP detects and addresses these issues by requesting retransmission of lost data, rearranging out-of-order data, and mitigating network congestion. Should data remain undelivered, the source is duly informed. Upon reassembling the transmitted octet sequence, the TCP receiver forwards the data to the receiving application, thus concealing underlying networking complexities from the application. TCP, widely utilized by various Internet applications like the World Wide Web, email, and file transfer protocols, prioritizes accurate delivery over timeliness, potentially resulting in delays to ensure data integrity. Hence, real-time applications such as Voice over IP may opt for protocols like Real-Time Transport Protocol operating over User Datagram Protocol due to their suitability for such applications. TCP provides a reliable byte stream delivery service guaranteeing identical byte reception order as transmission through positive acknowledgement with retransmission technique. By keeping track of segments, units into which data is divided for efficient network routing, TCP ensures error-free, correctly ordered transmission by reassembling segments at the destination computer's transport layer. The Transmission Control Protocol, TCP, processes data from a data stream by segmenting it into chunks and creating TCP segments by adding a TCP header. These segments are then enclosed in an Internet Protocol, IP datagram, and shared with peers. While the term TCP packet is commonly used, the more precise terminology specifies a segment as the TCP Protocol Data Unit, PDU, a datagram as the IP PDU, and a frame as the Data Link Layer PDU. When processing transmit data, they invoke TCP to bundle data from buffers into segments and request the Internet module such as IP to dispatch each segment to the intended TCP destination. A TCP segment comprises a segment header with 10 required fields and an optional extension field known as options. Following the header is the data section, which carries the payload data for the application. The segment header does not specify the length of the data section directly, but can be determined by subtracting the combined lengths of the segment header and IP header from the total IP datagram length specified in the IP header. The TCP header format encompasses various crucial components such as the source port, destination port, sequence number, acknowledgement number, data offset, reserved, flags, window, checksum, urgent pointer, and options. The flags section includes control bits like CWR, ECE, URG, ACK, PSH, RST, SIN, and FIN, each serving different purposes in managing the TCP connection. The data offset field determines the size of the TCP header in 32-bit words, ranging from a minimum of 20 bytes to a maximum of 60 bytes, accounting for up to 40 bytes of options in the header. The flag section also contains 1-bit indicators for specific actions such as resetting the connection, RST, synchronizing sequence numbers, SYN, and marking the last packet from the sender, FIN. The checksum field is essential for error checking of the TCP header, payload, and an IP pseudoheader, while the urgent pointer field is significant when the URG flag is set, indicating the offset of the last urgent data byte. The options field is variable in length and is determined by the data offset field, comprising option kind, option length, and option data components for configuring various aspects of the TCP connection protocols. The TCP protocol operations consist of 3 main phases: connection establishment, data transfer, and connection termination. The connection establishment involves a multi-step handshake process to set up a connection before the actual data transfer phase begins. Subsequently, the data transfer phase allows for the exchange of information between the communicating parties. Finally, the connection termination phase closes the connection and releases allocated resources. An operating system manages a TCP connection through an internet socket representing the local endpoint for communications. The local endpoint undergoes various state changes during the connection lifespan, including listen, SYN sent, SYN received, established, FIN wait 1, FIN wait 2, close wait closing, last ACK, time wait, and closed states. During the connection establishment phase, before a client connects to a server, the server must bind to and listen at a port for incoming connections through passive open. The active open, initiated by the client, sets up the connection through a 3-way handshake involving SYN, SYNEC, and ACK packets to establish bidirectional communication. On the other hand, the connection termination phase follows a 4-way handshake, where each side terminates its end independently with FIN and ACK segments to close the connection gracefully. A timeout period occurs after the final ACK, during which the local port remains unavailable for new connections. Additionally, various states like half-open can occur during connection termination. TCP resource allocation involves maintaining transmission control blocks, TCB, in a table to map sessions to operating system processes. Each TCB contains endpoint information, connection status, packet data, and buffers for sending and receiving data. The server can handle numerous sessions limited only by memory, while the client must allocate an ephemeral port for the connection duration. Failure to close unnecessary connections can deplete resources and hinder the establishment of new TCP connections. The Transmission Control Protocol ensures reliable data transfer through mechanisms like ordered data transfer, retransmission of lost packets, error-free data transfer, flow control, and congestion control. By using sequence numbers, acknowledgements, and various algorithms like RTO and DUPAX, TCP enables reliable communication by detecting lost data and retransmitting it. Congestion control is vital to prevent network gridlock, with TCP employing mechanisms like slow start, congestion avoidance, fast retransmit, and fast recovery to optimize data flow rates and network performance. Furthermore, TCP employs features like out-of-band data transmission to prioritize urgent data, window scaling to enhance performance on high-bandwidth networks, and selective acknowledgements, SAC, to improve efficiency in case of packet losses. Through TCP timestamps, the protocol can manage packet sequences, handle retransmissions effectively, and resolve ambiguities in case of reordered packets. Considering factors like congestion control, maximum segment size, and enhanced mechanisms like selective acknowledgements, TCP protocol ensures robust, reliable, and efficient data transfer over networks. A TCP connection is distinguished by a set of 4 elements: the source address, source port, destination address, and destination port. Port numbers establish different services and facilitate multiple connections between hosts. TCP utilizes 16-bit port numbers, offering 65,536 potential values for each source and destination port. Because connection identity in TCP hinges on addresses, connections are tied to a single network path, incapable of utilizing alternative routes available to multi-homed hosts. Changes in endpoint addresses result in connection disruptions. Port numbers fall into 3 main categories: well-known, registered, and dynamic or private. Well-known ports are designated by the Internet Assigned Numbers Authority, IANA, for system-level processes. Applications like FTP 20 and 21, SSH 22, Telnet 23, SMTP 25, HTTP over SSL, TLS 443, and HTTP 80 commonly use these ports. Registered ports are usually for end-user applications as ephemeral source ports when communicating with servers or identifying named services registered by a third party. Dynamic or private ports may also be used by end-user applications, but typically hold no significance beyond a specific TCP connection. Network Address Translation, and NATD, employs dynamic port numbers on the public-facing side to clarify traffic flow between a public network and a private subnetwork, enabling multiple IP addresses and their ports on the subnet to be managed by a single public-facing address. TCP has seen substantial improvements and suggestions since its inception with the publication of RFC 675 in 1974 and RFC 793 in 1981. Noteworthy clarifications were introduced in RFC 1122 in 1989, outlining essential TCP protocol implementation criteria. RFC 7414 provides a comprehensive list of 8 required specifications and more than 20 highly recommended enhancements for TCP. Among these is RFC 2581, focusing on TCP congestion control, a pivotal addition describing modernized algorithms to prevent congestion issues. In 2001, RFC 3168 was established, detailing explicit congestion notification, ECN, as a congestion avoidance signaling mechanism. Various alternative congestion control algorithms have emerged over the years, such as TCP Reno, TCP Vegas, Fast TCP, TCP New Reno, and TCP Hybla, diverging from the original TCP Tahoe algorithm. Multipath TCP, MPTCP, has been a continued project within the IETF, striving to enable a TCP connection to utilize multiple paths effectively for resource optimization and increased redundancy. Its usage in wireless networks allows for enhanced throughput and seamless handover capabilities by utilizing different networks simultaneously. Moreover, multipath TCP yields performance advantages in data center settings. In contrast to TLS, SSL, TCP Crypt does not directly provide authentication, but furnishes basic primitives for applications to implement. TCP Fast Open, an advancement published in RFC 7413 in 2014, expedites the establishment of successive TCP connections between endpoints by eliminating the traditional 3-way handshake through a cryptographic cookie mechanism. TCP offload engines, TOE, have been developed to address the processing power demands of TCP. However, integrating TOEs into computing systems proves challenging, necessitating extensive modifications to the operating system. The transparency of TCP's wire data exposes protocol metadata in clear text, allowing on-path observers to gather and modify information, thus compromising end-user privacy. This visibility and manipulability of metadata contribute to the ossification of TCP, enabling middle boxes to base decisions on or alter the transmitted data, thereby violating the end-to-end principle. Intermediaries often modify TCP metadata, with some paths encountering harmful effects. The extensibility challenges posed by intermediaries have constrained the design of protocols like MPTCP and hindered the adoption of TCP Fast Open in web browsers. Furthermore, the design of TCP as a reliable byte stream abstraction can lead to head-of-line blocking, causing network latency due to reordered or lost packets. To combat this, web browsers establish multiple parallel connections, increasing connection establishment costs and resource allocation. In scenarios where TCP is unsuitable, Alternatives like the User Datagram Protocol, UDP, are preferred for applications such as real-time multiplayer games, streaming media, and voice-over IP. Stream Control Transmission Protocol, SCTP, provides reliable stream-oriented services akin to TCP, but with added complexity and limited deployment compared to TCP. Venturi Transport Protocol, VTP, offers a wireless data transport solution designed to supersede TCP, addressing perceived inefficiencies. Different protocols like Multipurpose Transaction Protocol, MTP-IP, or UDP-based Data Transfer Protocol, UDT, are tailored to optimize network performance and throughput in specific conditions where TCP may be deemed inefficient. In the realm of TCP running over IPv4, the checksum computation involves taking the 16-bit one's complement sum of all 16-bit words in the header and text. To ensure alignment, padding with zeros is used when dealing with an odd number of octets in a segment. During computation, the checksum field is replaced with zeros, and then all 16-bit words are added with one's complement arithmetic, followed by bitwise complementation. The result is then inserted as the checksum field. A pseudo-header imitating the IPv4 packet header is utilized in this checksum computation, incorporating fields like source and destination addresses, protocol, TCP length, and others in the calculation. On the other hand, when TCP operates over IPv6, the checksum computation method varies. In this scenario, the pseudo-header for checksum calculation emulates the structure of the IPv6 header, including fields like source and destination addresses, 128 bits each, TCP length, 32 bits, zeros, and the next header. Depending on the packet's contents, the destination address can differ if there is a routing header present, affecting how TCP utilizes the address information. Furthermore, the checksum offload feature offered by numerous TCP IP software stack implementations allows for hardware assistance in computing the checksum before transmission or upon reception, potentially minimizing CPU workload and enhancing overall network performance. However, this method may lead to packet analyzers flagging invalid checksums in outbound packets intercepted before reaching the network adapter, despite all packets transmitted by the adapter having valid checksums. This discrepancy in reporting may also arise in scenarios involving virtual machines on the same host, where a virtual device driver could opt to skip checksum calculation, relying on later calculations by the host kernel or physical hardware.